this lecture I'm going to call Mercury Tectonics Mapping Lecture. So the goal for this, if you were taking my planetary geology class, is that you're going to learn to recognize thrust faults and normal fault related structures on Mercury, and you're going to be able to incorporate those structures into your geologic maps. So let's start. We're going to look at Dario crater on Mercury. That's the map you have here. So if you have a packet at home, go ahead and pull that out. You've got a scale bar down in this corner where this is 20 kilometers and north is up. All right, so what you should notice is the difference between this and a regular impact crater. So if we have a regular impact crater, like let's look at maybe this one in the lower left-hand corner, we have a rim that is solid and complete all the way around. Maybe there's some terracing coming down the sides. If it's a complex crater, there might be a central peak. And then we might see this smoothed out floor either from impact melt or flooding after impact. So when we look at a crater like Dario crater, and one reason I'm using craters to teach the tectonics of Mercury is that it gives us an ability to really see the tectonic structure or the fault that's cutting this crater. So for a few reasons. One, because we know an impact crater should be circular with a continuous rim. And as you can see over here, and maybe over here, and down here, this structure, this fault, is offsetting that rim. So we don't get a nice circular shape. Same thing over here. We've got kind of a break in that impact crater rim. So impact craters are a really nice place for us to look at faults and tectonics because we know what the landforms should have looked like before. We're going to follow the same steps that we've been following so far in planetary geology this semester to map this impact crater, but then we're going to come in and talk about the structure later. So, for example, in your worksheet of map units, you're going to define at least 3 units, and then you're going to define the structures that are over those units. So we'll name the units and color them in. We'll write our description, which again, remember, descriptions are observations. And then if we want to follow it up with an interpretation, then we can make that choice later. And we want to look at those data types used. So here our data types are going to include the MDIS image, which is the Mercury Dual Imaging System black and white image. But we will also be using the enhanced true color image of Dario crater and some topography. All right, so let's start out. Let's try to classify what units on the surface there might be just using the black and white photo. So the MDIS photo. All right. So we tend to look at texture, tone, elevation, and then maybe process. So if there's a different process that played into making that surface. So for me, looking at this image, I see a rough texture outside of this impact crater that looks to be a higher elevation, and we can check that with topography. And it's more heavily impacted, so an interpretation could be that that surface is older. But there are some regions of smooth topography, like down here, this looks, it's still high elevation, but it looks a little bit smoother. And it's got a new impact crater, fresh impact crater on top of it. And it looks like there's a smooth area down here, and maybe up here too. And maybe up in here. Now, do you see how, if you're looking at this image, there's kind of a blocked out area of smoothness right here? Those clean lines and sharp edges tell us that that's a data effect. That's not actually smooth topography. So the way that I'm saying that this is smooth topography is I'm actually looking at this right here, this little corner, and seeing that there are fewer impact craters and that that surface looks a little bit smoother. So outside of this impact crater, outside of Dario, we might have 2 main units. And then if we look inside of Dario crater, it looks like we might have just one. Everything looks like it's cratered pretty evenly. It's all relatively low to medium topography. It's smooth. It's speckled with secondary impact craters, but they're not big necessarily. We've got these two that are a little bit larger, but maybe there's only one unit inside of this crater. So we've got 3 main units so far. Let's look at our other data types and see if we have any new observations. Okay, again, this one's elevation, so let's start there, or elevation or topography. So within the impact crater, we can see that there's actually kind of a bimodal distribution in elevation. There's this part in the middle, kind of a weird mushroom shape. And then there's these edge parts right here that are a little bit higher topography, but they're still smooth. Outside of the impact crater, we can still see that really rough terrain, but those areas that we said were a little bit smoothed out are a little bit lower in elevation. So just to remind you here, it's white is the highest, then brown, then red, and we would continue on down all the way through the rainbow to blues and purples to go toward low elevation. We just don't have that here. So this map, or this image, is suggesting that maybe we have another unit to add. And that unit that we would be adding is this high topography or higher topography within the interior of the impact crater. One thing to look at too when we go to map structure, you'll see that there's a really sharp contrast here between a white and brown unit and this red right here. That nice sharp contrast isn't necessarily because this is white from white, like up here. This might be white, like a lighter color, just because of illumination. And the way to check that is to look back on your black and white photo. So see how this is a little bit lighter? When this topography gets overlaid on top of that, this area is going to show up a little bit lighter. That doesn't mean that this is as high as this topography. This is just an illumination effect. The same reason, like if you look at the inside of this impact crater and it's white, that's not white because it's super high topography. That's white because of an illumination effect. The sun is coming in from this way. Okay, so now we're up to 4 units. And then if we look at enhanced true color, we can see that there's these really, really bright areas inside of that impact crater. And so those really bright areas inside the impact crater are newer, fresher impacts. So really, really bright stuff on enhanced true color tends to be younger. And that kind of supports our interpretation that down here, this smoothing might be related to a young impact, where you have a central peak. And then you've got kind of a spray of ejecta, making that enhanced true color a little bit lighter. So let's go ahead and define our units, and then we'll start mapping them on our image. So let's start with the really rough stuff outside of the crater, because that tends to be a little bit easier to identify. So unit 1, I'm going to call rough terrain. And I'm going to describe it as being rough, high elevation. Let's check tone for a second. So I'm going to go back to enhanced true color. Here, if I'm looking at this area, it's kind of like mottled dark and light. So medium tone to mottled. Lights and darks. And we know that it's got a lot of secondary impacts. So many other impacts. And this is where we would put in our interpretation if we wanted to. So I'm going to interpret this to be old terrain. And the data types we used were all of them. So we used the topography, we used enhanced true color, and we used the MDIS black and white. We used all 3. All right, another unit we identified, and let's stay outside the crater, is the smoother high topography. Okay, so this was smoother, high elevation. Let's see. It was characterized by fresher impacts. And I'm going to interpret this to be resurfaced through ejecta. So ejecta have basically covered that surface, and so we see kind of a new surface. And we used all the data types for that. The third unit we saw was inside of the crater, and it was low, smooth topography. And we said that it was smooth. It had small craters that were bright and young. It was low topography, and it was inside crater. Sorry about my phone, y'all. We can interpret that to be crater fill, or crater volcanic fill. And then we're going to have medium smooth topography. So medium elevation, I should say. That medium elevation smooth topography was this unit right here. So it's going to be all the same things as this. Small craters that were bright and young, but it had medium topography. And it was inside crater. And my interpretation is still that this is volcanic fill, but it's going to be uplifted somehow. And we used all data types. Now, when we make high topography, when we start with a unit like this, a surface like that, and we lift it up, that lifting up process is kind of a shortening process too, and that's caused by thrust faulting. So if we looked at a crater that would be a circular impact crater, and then we looked at this crater, we would find that this one is smushed just a little bit. And it's smushed or shortened in that direction because of this thrust fault that's creating this high topography. Okay. So the structure we have with thrust faults, and we can give a quick description of those two. So, or rather, we can give a description of the properties of the surface that they produce and a little bit about their orientation. These faults seem to be running northeast, southwest. So we can talk about their orientation, northeast, southwest orientation. We know that they cut the crater and some of the surrounding terrain. If we look on the MDIS image, it looks like there might be another one running northwest, southeast, but it's not as prominent. So we could say a northwest, southeast orientation of less prominent structures. And that it's producing elevated topography. And again, we used all data types to determine that. Okay, let's go ahead and make our map for this. So using those units, I'm going to find my boundaries. I'm going to define the outer boundaries first and then work my way in. So down here, I have kind of a smoothed unit. It goes right up to the crater wall. Again, where you're not sure, it's always okay to dash. For the sake of visibility in the video, I'm not going to dash unless I really feel like I have to. Stay outside or on the rim if I can. Okay, I've got some lighter low topography units out here. And some up here. Okay, now I'm just going to pick a color for that. Right, now I've got this kind of rough outer surface that's outside of the impact crater. When we map, we want to fill up the whole sheet. I'm going to be careful right here because this looks like smooth infill on that little other crater. I'm being careful with that because that actually would be classified in a different unit. Alright, now within the crater I have to go back to marking out my topography. This was my relatively high smooth unit. And then I've got the low smooth unit. Make sure I get a boundary on that. Okay, now it's time to actually map structure. Sometimes you'll find that the structures divide units, which is kind of the case here, but sometimes they don't. So let's go ahead and mark where we think that this fault meets the surface. To get a good idea for this, I'm going to kind of give you a cross section on this topographic map. So let's say that I went from A to A prime. I wanted to see the elevation on this surface. Got low, then I come up, and I drop back down. This raised topography is produced by a thrust fault under the surface. When we see a really, really sharp boundary like we do here, that we interpret as the place where the fault meets the surface, or the fault scarp. So this is usually called a scarp face, but it's actually the front of a fold. So Pretend that that's a fold right there. This is the front slope of a fold. And the actual scarp is whatever little bit of topography is produced by that fault meeting the surface and moving all of this up. And so that scarp is going to grow over time. So we want to mark this location as being a fault. Now over in a 3D space, okay, what we're actually doing is marking this boundary line. And we want to put little triangles on here on the high topography, on the hanging wall. So in a thrust fault, a hanging wall moves up relative to the footwall, and we want to make sure that those little teeth go on the hanging wall. So here, I'm going to take my time. Again, it might feel repetitious because in this particular mapping project, it's more or less repeating the unit boundary. At least it is for down here. As it goes up here, it looks like the fault might actually continue. I'm going to dash it because I'm not sure. And then I'm going to put my teeth, I'm going to draw those on the high topography side or on the hanging wall side. All right. Now I'm gonna do this other side over here. Looks like fault comes down. I don't see it continuing down through here. And then we've got some kind of other structure here, but it's less clear where it is, so I am gonna dash in that boundary. I think it kind of stops there. Maybe that's the hanging one. And it looks like it continues out this way, maybe. Tectonics can be really, really challenging, but that's also why I like doing it. All right, so this is our map that we end with. So in the part 2 of this video, we're going to be going over normal fault mapping. Thanks.